Assalamu alaikum. I am Danish Bhatti. I'm a movement disorders neurologist currently working in University of Central Florida, um, College of Medicine as Education Chair for Neurology and Associate Professor. And I'm the Director for Neurology Clerkship and the Neuroscience course at the College of Medicine. It's my pleasure to talk to you about the implication of artificial intelligence in medical education and helping improve the role and work of medical educators and medical education in general. This is a topic very close to my heart, and I've always been a fan of innovation. So I will start by giving you a basic introduction of various concepts within artificial intelligence, a very high level idea, so that you know what we are talking about. And then we will look at some of the use cases for artificial intelligence in medical education. And then I would spend most of the time in the two use cases where I'm doing my work and show you in the web browser some of the work I've been doing in trying to use AI in medical education. So let's get started. Artificial intelligence is a very large topic or a word. Oftentimes, when we are talking about AI, we're talking about a subset or a simple component or one of the components of AI. So, intelligence in general means learning. And artificial intelligence basically means that a learning that is happening non organically, meaning that we have created some process that can learn. And learning is basically a series of rapidly generalizing conclusions. So you take simple rule, you apply in one setting, but then you generalize it to other settings, and that's what you are learning, and you gradually optimize it so that your predictions on the different settings are improving, and that's really what is learning. So artificial intelligence started early on with the first computer with Alan Turing, and there was already some test or Turing test proposed for what would be a true artificial intelligence. A very simple test from at that time, more of a behavioral test, where it was that the concept of the test was that any intelligence that can interact with a human can fool human into believing that they're talking to another human, then they will consider that as an artificial intelligence. The concept of artificial intelligence struggled for a long time until they figured out this concept called machine learning, where they design a way where the learning can happen automatically by a computer system. And then even that struggled for a long time to create something meaningful, although some good products came out of just general machine learning, such as the first program to beat chess for human, Gary Kasparov, that became very famous. But the real breakthrough in artificial intelligence happened with the concept of deep learning, which basically was an application of what we call artificial neural networks, or ANNWs. And I will summarize all of this in the next few slides. So, what is machine learning, or how is that different from what we typically think of a machine work? In a traditional machine work, you put in a data into a machine which you want to be analyzed, and you give a clear set of rules or logics to the machine, which is called programming or program, and it basically then uses those rules and logics to analyze that data, and it can do it very fast. The simplest example will be a calculator. You have given all the rules for calculation to a calculator, and now it can process huge amounts of data very efficiently, very fast, and looks impressive as it is, but is not considered intelligent because it must remain within those rules or set of logics that you give it to. It cannot create any new rules or logics. And that's where the machine learning comes in, where you are just giving data and you're giving some information or even no information and asking it to create its own rules and set of logics by looking at the data. And that's what's called machine learning, and it is creating its own rule sets of logics, and now it can apply those to new data, and it can continuously improving, or you can freeze it. You can say, okay, keep these rule sets and logics, don't make any new, or you can say, okay, keep learning and keep producing new rules or sets of logic, or refining it. And that is what is machine learning, with which basically is the breakthrough required for computer to generalize information or do a true learning. And before, AI was always trying to go through the traditional programming route, always keeping up, giving more and more rules and sets of logics, and to try to create what looked like an intelligence or mimicked intelligence, but it was always just following rules or sets of logics you have given it. Machine learning can be of very different forms or distinct ways or methods. This is more technically important for someone writing the code or process of an algorithm for machine learning. And you can have it supervised, meaning that you give it some information on what is right and what is wrong, and then it uses that information to create rules and logics which are more detailed. So you have given it answers on a learning data set, and it uses those answers or labels to then create new rules, and it creates its own rules and logics. That it keeps on improving. You test it again, and then you give it more feed data, and so on and so forth. And it uses these three methods: regression, classification, and ranking, to try to come up with its rules and logics. You can do unsupervised machine learning, where you just sort of give it a lot of data. Don't tell it what the data is, so don't give it any answers or labels. You ask it a question, you get the answer, and you give it a feedback, what's the answer, right or wrong. And based on that feedback, did it get it right or not, it keeps on creating its own rules and logics. And it looks, again, at methods of ranking or anomaly or clustering or recommender and various different things to try to come up with its rules and logics to get you the right answer that you say, yes, it's right. So this is kind of a workflow of a machine learning algorithm, whether it's either using deep learning or artificial neural networks or not. That is secondary, but the concept is the same. You have a training data set, which is either labeled or not labeled. You feed it into a pre-written algorithm or codes which guide computer how to do the learning, and you give it either labels. So in a supervised learning, so for example, you give it images which are labeled. Some are apple, pear, tomato, cow, dog, and horse, and it creates a model, meaning that it creates some rules or sets of logics on that information that's coming to it, and then you give it a test data to see did it get the answers. And based on its accuracy, you can either go back and start the training data set again, either increasing the labels or amount of the pictures or images, or you can give that information from the from the test data set back to it to say what it got right, what it got wrong, and then it will further improve its algorithm or model. Is it called a trained algorithm? Is called model. Trained algorithm has different adjustments done to it, and that's why it is called a model. It's not that raw code that initially you started with or not. So a specialized form of machine learning, which is now becoming the major form of machine learning, is what we call artificial neural networks or deep learning. And it uses the same concept as a neural network, meaning that there is a cell or a neuron or an information area or a piece of code, which is linked with hundreds or thousands or tens of thousands of other nodes or cells or data pieces of information. And information, as it runs from one of these cells or node to the next, alters the behavior of the next node, and that's what the learning is happening. So you have nodes here in colors, blue, which is basically just information pieces in some rules and logic. It gives it to the next node, and that next node is getting information from multiple previous nodes, and it is kind of assimilating or putting together that information from various nodes to come up with its rules and logics. And multiple nodes are creating their own rules and logics, which then feed into the next layer and the next layer and the next layer. And you can make it as complex as you want, and all until the final layer, which gives you the output. And the output layer is basically now taking all that processing of information that has happened to try to give you the final answer. And the nodes adjust their value of the nodes input coming into it, which is now called weights or weightage, and you will see that term used very often. And it's almost like how a neural network processes the information coming in to give you an output. So let's take an example. Here's a picture of a cat that you have given it to learn. It takes each fragment of this picture to feed into one of the nodes, and that node goes through different layers of processing. Okay, what information in this fragment needs to be for may give it that it is a cat, or what we call a probability. So it says, okay, based on the color of this pixel and the information in this pixel, do I think it's a cat or not? Yes or no? And that information is now going through all these fragments into one node. They go to the next node, they go to the next node, and each of them are adjusting their probability. What this node concept is doing is that the pixel in itself is not valuable enough. You need to know what is around it, and then what is around those around it, what is around those around it, until you hit those margins of boundaries. So the boundary of the cat image, as separated from the background, is valuable, as well as the eyes, images from there, the nose, the mouth. So each pixel has a value, and that pixel value combined together influence or interacts with each other's probabilities of whether this is a cat or not. And that's what this algorithm is. Its training is learning that what is the value of this pixel when that pixel is this way, or that pixel is this way, or this pixel is that way. So that is that neural integration happening, as you can see in this connected layer interface, is that each node or each that is getting one information from one pixel originally is trying to create a weight of that based on the other pixel, and then the integrators are taking weights from all of these and trying to come up with a probability calculation. And in the end, the output layer, you can force it to say, give me all or none probability. Is it a cat, is it a dog, or nothing? You can force the output layer to give you probabilistic. So let's say the probability comes out to be 51%, it's a dog, you will call it a dog. Or you say, I want a probability of 70% before you call it a dog, or 80% or 90%, or whatever. You can set all these output parameters in terms of probability, or the raw output will be, okay, there's a 70% probability it's a dog, 30% that it's a cat, or 70% it's a dog, 20% it's a cat, 10% that it's none of these two, or whatever. You can train an algorithm to know all the animals, or all the four-legged animals, so like horse and donkey and all of that, and it give you a probabilistic answer that this image is this much probability this much probability this probability this. It can reach close to zero, but maybe it would never reach zero for four-legged animal picture. So now you can use the same concepts in locating image. So this algorithm was trained to figure out which area or pixels in the image are vertebra. So it's trained to figure those out and then box it. So it's boxing on these vertebras to say, I think these boxes are the vertebrae. You can also further train which one will be a thoracic vertebra or cervical and all that, just based on X-ray image, and a lot of extra data with labeling initially or unsupervised learning. And then based on the arrangement of that boxes, you can say, okay, now tell me abnormalities of the curvatures. What is a normal curvature? What is an abnormal curvature? What type of abnormal curvature? And you can use it doing the heat map or the boxing, and then you can figure out that can it read the vertebrae on the images. Same way you can do it for lungs. lungs, you can do it for heart. You can train it to say which pixels belong to a heart, box it into or outline it, and then tell me what abnormalities you're seeing. Is it a larger heart or a smaller heart or rotated heart, and so on and so forth. Now, coming to medical education, another important breakthrough was trying to do the same thing with language. And what we wanted to solve with the language was that if the question is this, what is the answer? Now, for that, it has no inherent concept of vocabulary or language like we do, associating with it with a thing or with an image. That will be a multimodal AI, which is still under work or a process. When it says dog as a word, it is just a word dog, or alphabets dog. It doesn't have an understanding that dog means dog. That is the multimodal AI that has not been broken through yet, and that will be the general artificial intelligence. Right now, the language intelligence is called natural language processing. It's called natural for the language, not for processing. So it's a natural language which is being processed. Natural language means that language that humans use, while a non-natural language will be the language that computers use, for example. So a natural language processing is a way to process the information even though there is no understanding. So it doesn't know what is a dog, what is a cat, what does animal mean, what does street means, but it can process the information. So how is it doing it? It is basically again creating a probabilistic relationship model that if a certain word comes in a sentence, then what is the probability of the word before and after? And as I've showed you in the images before, the probability is dependent not only on that word itself, but is also dependent on every word that has come before it to say what would be the next word. So just saying animal, what would be the word after animal? That's a simple psychological test sometimes we do. I'll give you a word, tell me what the word you can think of. And we can do different psychological testing for humans to look for word associations or word affiliations. But here, we're not looking for that, right? We want it to answer something when we ask a question. And for it to answer, it needs to know that any word that you have asked, what is the probability of the word in the world in general. So if I say animal, what am I asking from the computer model? For it to predict that, it needs to say, what have I asked before and after that word animal? And in general, in the world, where is animal used? What is the probability of other words happening before and after? And then based on that, it creates a new probabilistic map of, okay, what words should come out. So it's going to create a sentence, and it needs to predict a probability of each word in that sentence based on the information I give it. It may be just animal. If you say just animal, now it has more freedom of choice. It can use that animal with all the context it has, either with you in a conversation before, or any information given to it that the target is medical students, for example, or something like that. And then, if otherwise it's just a random picking up, you say animal, and it will randomly pick up any other association with it. But if you give it a sentence, and then say, okay, respond to the sentence, now it is going to create probability of each word in the sentence is going to generate based on the information you gave, and now all the information has been trained on before, and any other context you have given it. But and then it's just basically calculating probability of word should go where. And then create a sentence. Now, it looked like a meaningful sentence to us, but what it has done is basically just give us a probabilistic representation of alphabets or characteristics or sentences. It doesn't even think in words, to be honest. It really just thinks in alphabets. It thinks in what is called token, and a token is a combination of 4 alphabets or characters, it could be spaces too, and it's just giving you those probability prediction of those alphabets on how they should line up and where the spaces should be. And then it looks meaningful to you because it has learned enough to really predict what should be where. And that's all it is doing. And you can go into a more detailed discussion of it on the link here on jalamar.github.io/illustrated-transformer. And there's a long, good discussion on how these probabilistic calculations are done by what is called a transformer. Transformer was the breakthrough in terms of language or alphabet probability calculation to give you an output based on the input. And that is what has led to the ChatGPT or generative pre-trained or transformative text or transformers. You can, of course, get more resources on learning about AI on openai.com/blog, more around natural language processing, and developers.google.com on machine learning, and has a crash course and other details that you can go and look at. Now you know that what are the general capabilities of a deep learning trained algorithms or models, either on image analysis once it has been trained, and on word predictions based on the predictive training a transformer has gone into or from the information it gave. And training counts a lot because it's really adjusting its weights on output or prediction based on the information you are giving it, either labeled or unlabeled. One last concept I want to say before I jump on to the use cases for AI and machine in medical education is the level of role an AI plays has been divided into 5 levels. When we think of level of AI, we're immediately jumping to level 5, which is full automation. That AI or artificial intelligence does everything on its own, and we don't have to do anything to it. Not even provide an input; it just gets the input from the world, just like we do, listening to conversation or looking around at the world. However, an AI can perform roles of augmenting human activity at three other levels before reaching level 5. And that is very important to learn because we are still ways away from level 5, but we should not ignore the advantages of level 2 to 4, which I will be showing you in our use cases. So level 1 is where there's no AI involvement and it's just human only. In level 1, you can say that maybe calculators are still in level 1 or not, because at least decision making was already pre-programmed into the calculators by the human. Level 2 is what is called shadow mode. That AI system is evaluating the situation, creating an output. You are not using that output to make the decision right there, but you can go back and analyze that output and what you did and try to compare the two and learn some lessons from it. So human learning later on as more of a analysis or feedback. Level 3 is where the AI assistance runtime starts, where the decision making is influenced by the output of AI. Again, AI is not making the decision, it's just showing you how it is perceiving or creating answers, and you pick and choose what you want to create, to keep from it, or use or not use. And that's level 3, where most of the computer-aided decisions or AI-aided decisions or computer-aided diagnostics and everything in medicine and in general in the world is at right now, is around level 3, including self-driving cars and so on and so forth. Most of them, not all of them. Some have reached level 4. Level 4 is where you are not selecting all the decisions. You are selecting some of the decisions, but you're allowing freedom for AI to take charge of some decisions. So some level 4 autonomy has reached by AI. So for example, an AI is taking decision on when to brake or not to brake. Now, it's not giving you the decision and you to choose. It is making the decision for you for automatic braking, for some drone flying, some even image sortings and pre-screenings of images and so on and so forth in healthcare and outside of healthcare. But still, it is taking only the most mundane and most reliable decision, while the complex decision or the challenging decision, it is still leaving up to you. And level 4, of course, can be anywhere from 10% automation to all the way up to 90% automation. And there is a lot of room in that level 4. Level 5 will be where it does not need any input from human anymore. And so far, we don't have any good commercial examples of level 5. There may be research examples of level 5, but no true commercial examples. So now let's focus a little bit on the use cases of AI in medical education. I will give you 3 case study examples. Case 3 or study 3 is where I have focused on mostly, and I will show you some details of my projects there. So let's look at the case study 1, which is the virtual patients and simulations in medical education. So a lot of medical education is teaching students how to generalize based on certain cases that they see. And the more cases they see, the more they're able to generalize or fine-tune their own learning, their own neural networks. And that, is dependent on them seeing a lot of clinical cases. The problem is that often when they're seeing clinical cases, they are also influencing or at least affecting the decision making of that clinical work, and that sometimes can lead to delay in care or errors or damage to the patients or so on and so forth. I don't know of a good data because there's always supervised learning in medicine, but there's always a risk that students can do something harm, give a wrong order. So a lot of time orders are only allowed to be given by residents in training who have graduated medical school and so on and so forth. So autonomy is given very late. One solution on speeding this up, or the other problem is that if your learning is now dependent on the cases that are coming in to that clinical environment. So if you're in a clinic, you're in a small hospital or a medical school, you would only learn based on the cases that present to that environment, and you may miss all the cases that you are not seeing. So that's why complete learning for a full well-trained specialist consultant can take more than 10 years. Now, of course, this could speed up if you could see more cases, or in a busier hospital, you spend more hours, and so on and so forth. But not everybody gets that opportunity to work or study in a big enough busy hospital which has the full variety of all the clinical cases. That has been strength of some of the medical centers and institutions. However, the other centers and institutions are trying to catch up by creating virtual patients. Initially, before the AI, we started by hiring actors and writing scripts for them. There was a problem that there's only so much details you can put in a script and only so much acting an actor can do. But now you can create these AI-based models that can interact with you. I give an example over here, dr.gupta, dr.gupta or gupta.ai. You can go to this website, test it out. Is for patients' self-educational learning, but you can also use it for medical education and learning. There's also Kaplan's iHuman, which is our patients, which are AI-generated answers. So it's not fully scripted. So far, most of the VR or simulated cases were scripted, that you're writing the exact answer in situation that dummy or that computer model should give. And AI can help you now, not having to write scripts, and on runtime create answers which are different every time you interact with that human and make it more human-like, simulated dummy or computer model or graphic. And so there's also body interacts program, learn with virtual patients, but all of these are now non-scripted, and they can learn from the whole plethora. So you need to train, for example, on a cardiac patient. Then you can have a model that is fully trained on all cardiac diseases and illnesses and patients and all stages of illnesses, and you can give it a scenario now, or the student can give it a scenario that, hey, you're a cardiac patient of, let's say, 55 years of age, male, you have this background, you have you're early in the disease, you're late in the disease, how many years of disease, were you diagnosed, undiagnosed, you have had complications before or not, what medications you've tried, everything can be just given it to the model immediately without having to worry about that when writing scripts. Writing scripts then forces you to just stick with that script, and you cannot change the setting every time you interact with that model. And that's why those have been very few and not very commonly adopted, but AI will solve that problem. So you can have all these patient simulations and patient clinical environments and test taking that can happen, and that can provide you with a wide variety of learning now that you would not have seen unless you are in certain specific centers in education. Another interesting use case that I wanted to share was this use of AI in research and study aids. So writing good papers, writing abstracts was a skill that required a lot of effort and training. Those few students who learned it early were already doing great, but that will go away. I showed you 2 examples of website. You can go and check them out. Jenny.ai is a place that helps you write research papers by supporting your writing through AI. So it's kind of helps you how a paper is written if you just give it the concepts that you want to write, either a review paper or abstract, or even if you have research, you don't know how to write a background or introduction, Jenny can help you with that. Can help you write methodology, proper language to use, proper ways to describe it, can even guide you what information you need to put in to get you information. Similarly, Paper AI is another product which is doing this, probably many others. These are just 2 that I kind of found or have interacted with. Similarly, research can also help you figure out how to design your study. So this is just paper writing, right? But in terms of how to put a protocol together, you can go to something very advanced like Google DeepMind or IBM Watson and answer clinical scenarios, what questions to ask or how to design your studies. Or you can go to something like ResearchGate, which has kind of a learning compendium of all published research. So you can ask questions from it. Okay, what research has been done on this? What topic is still missing? What are other experts saying that are the next questions to ask in this study? So let's say you have a patient with, asthma, and you say, okay, I have asthma patient, this kind of patients I have, what research questions can I ask in designing a study, and what has already been answered or what needs to be answered. And there are tools like ResearchGate which have full knowledge or information of published research, can answer you before learning a skill of how to analyze the published data to come up with a research question used to be an extremely difficult skill to learn, and that's really where the full consultants or research advisor shined in telling you he knew in his area or field. For example, let's say they are experts on Parkinson's disease. They can tell you what are the current burning questions in Parkinson's disease that they have spent 20 years trying to master that topic or question. And then finally, I wanted to show you the work that I've been doing, which is a third case study, which is my interest, which is using AI to improve on student assessments in learning. And we know assessments used to be to say, okay, this student has reached a certain stage where they're ready to move on to the next step, whether it be admission to medical school, graduation from a medical school, graduation from 1 year of school to the next year, into residency, graduating residency, getting a board license, and continuing medical education, everything required assessment. But we have now figured out and learned that assessments are actually a very powerful tool for learning itself. And they created a whole concept of what is called formative assessment that forms your learning. So just taking questions or assessments help you master that information even more or learn how to think critically in that given situation. So there are various ways to it. Let me show you 2 projects that I worked on. One project that I worked on was to see, can large language models, LLMs like ChatGPT, natural language processing AI models, can they reliably evaluate and label a medical student's H&P that they wrote as part of their clinical rotation, what we call clerkship. And can these assignments be evaluated by LLMs, large language models, this AI like GPT, and can they be graded on a standard rubric? And can they also work with unfamiliar tasks? Like, for example, can they also assess the student's empathy towards a patient, how empathetic they are, the student's understanding of the social constraints or limitation, and what we call the evidence-based medicine decisions, and so on and so forth. And we found it very useful, and we published this data. Let me show you how it looks. I'm not going to show you the product that we are working on, which is more task specific for this use case, but I'm going to show you my similar exercise in a general publicly available model that you can also evaluate it. So let me take you to a browser, and I have put it available publicly for you to also review in detail, because I cannot show you all the detail right now. So you can go to in a browser at bit.ly/AI-in-med-ed, AIINMEDED. So I'm going to pull up my browser here in a minute. Give me 1 second. Here's a browser, and in this browser, you are seeing some scoring at the bottom of a history that I gave to the ChatGPT. So ChatGPT is giving an interpretation on grades for data gathering, what was good, gave it full score 30 points, medical reasoning, gave it full score 60 points, and diagnostic and therapeutic plan gave it 8 out of 10 and gave it a competent degree. It then also went on to also score them on patient-centeredness on that H&P that they wrote, history and physical. high value care, which is basically that are you using your resources most efficiently, and give it novice on both of these or a score of B on these two, and give some verbal output. One of the problem I'm seeing is that a lot of these outputs on the rubric scores are usually close to 100 because the rubrics are not defined well enough. This was the HNP that I copied in for this rubric. So if I go back up, this is just the HNP that I gave it. I also then worked with this to try to identify, can it give individual detail or recommendation on how to improve these HNPs that they have written, and provide some information around that before it just grades. So here are what you see as suggestions for improvement. It gave in suggestions on how they could have done better on patient-centeredness in this HNP and high-value care. Similarly, suggestions for improvement on diagnostic plans, like here, that on each problem, what they could have done more in terms of nutritional counseling, stress management, in terms of continued management of lifestyle management of hypertension, medication adjustment for chronic migraine with aura, sleep consultation, lifestyle. So you can really, if you ask the right question, you can get a lot of information on recommendations on how to improve HNP for the student. And when you do that and then ask it to grade it, it then becomes a little more strict and gives a more coherent grading. So now it's giving score of 24 out of 30 incompetent, 48 out of 60 competent, and then 8 out of 10 on these different components, because it has taken some time to analyze it and give suggestions. So the takeaway message for this that we are working on is that the problem with LLM is that it is very predictive, that its output is just a prediction based on information you give it and general information it knows or what it has been trained on. But the prediction it will do will become better and better if you ask question with more information and better, more apt information that is relevant, more relevant information, because it will take your information to calculate the weights of the output, right? It has an internal weightage model. When you give it an input now, that model is already trained and locked. It's not going to adjust its weights based on your input, but it will take your input to calculate output using the model. So the output is directly dependent on and related to the input. So this whole concept of what we call prompt engineering is becoming more and more valuable, which is basically a prompt learning, that how to do a proper prompt is becoming more relevant when using these LLMs or large language models in medical education. You can go to this website and review it in more detail. Another relevant use case that I have been working on is using assessments or creating assessments for medical educators by students. So that's a very challenging task. It takes a lot of time to create a good assessment, a good multiple choice question, and that's why questions or good MCQs or multiple choice questions are always in demand, and they're hard to find, and it's very difficult for faculty or educators to sit down and write them. Can LLMs, large language models, help you generate questions that are somewhat useful? Again, we are thinking about level 3 and level 4 autonomy, so partial automation, not a level 5, a complete automation, because we are not there yet. So level 4 will be where the output then has to be further improved or selected by the educator or the human to see what is useful, what can be kept, what should be kept, and what is not useful and can be removed or changed. So let me again share a website to show you an example. The idea is, can we create an MCQ generator which takes any input, have a certain settings on what kind of question needs to be generated, and the input can be a PowerPoint lecture, a Word document, or a PDF, and then generate output for you, which are useful questions, which have a question stem, which have distractors, has a right option, and then some detailed explanation to give you an answer. So let me pull up this website again. Give me 1 second to pull it up and show you what it would look like. So this again is publicly available. You can go to this website. This is called quizmd.ai, and you log in just by using your Google account. So I'm going to use my Google account to log in. And here it is. There's a generator. You can select the settings. Then this is gradually getting better as we learn more and more settings we should give you. And you can just simply upload a document or just copy an information to get your questions. You can see my history of few questions I've been generating today. Or you can also see some shared examples in Explorer. You should have access to that too if you log in. And these are some of the questions that have been previously shared by different generators. So let's look at these. A radiologist that generated some question. It generates a clinical case based on the information you shared. It is not exact text or information from the document, and that will not be AI. AI is taking the information in the document, understanding what that means, and creating from a general world of information and information. So that's a clinical case generated, labels its difficulty, Bloom taxonomy classification, ask a question, gives you option, and then if you click reveal, it will give you what is the right answer, and then give you an explanation of why the right answer is the right answer and why the distractors were not correct. And it can give you question after question after question. When you upload the document, it generates certain amount of questions, and then if you like some of those questions, you can keep it. You can actually download those questions by hitting the Word document export or an Excel document export, and then you can edit those questions to the final version that you would like it to be. And then and you can delete what you don't like, and you can keep what you like. Again, all these questions are not going to be perfect. There will be mistakes in it. There will be questions that are not relevant or not are too difficult or too easy or too straightforward. Some distractors may need to be adjusted. So the goal with this tool is to be 80% there, to be able to answer questions, create some draft of questions that can be then further refined by human. So a level 4 autonomy, and then final product will be used by human. And eventually it may reach a level 5 autonomy. So I thank you so much for your interest and for your attention. You can reach out to me by writing me an email, or you can find my YouTube channel where I have recorded more information around these topics. And you can also connect with me on LinkedIn by finding me on there. So I thank you again very much for your viewing of the lecture. Thank you.